So, if you've ever stared down a massive physics problem and wondered how we can pinpoint exactly where unseen forces are at their absolute strongest, you are in the perfect place. Today, we're going to demystify a classic electromagnetism problem, finding the electric field generated by a charged ring. But listen, we aren't just going to skip to the final answer. No way. We're going to harness the sheer power of calculus and break this down line by line to find the exact point where that electric field reaches its maximum peak. It's an absolutely beautiful journey, from a physical concept straight into pure mathematics and then right back to physical reality. Let's get into it.
Okay, real quick, here's our roadmap for today. 1. The charged ring setup. 2. The maximum value problem. 3. Setting up the derivative. 4. Solving line by line. And finally 5. Visualizing the peak.
All right, Section 1, the charged ring setup. Before we touch any calculus or look at any wild fractions, we have to establish the real-world geometry. Understanding the physical scenario is literally everything here. So imagine a uniformly charged ring with positive charges marked all the way around it. It carries a total charge of Q and has a radius of R. Now I want you to picture a line running straight through the exact dead center of that ring, perfectly perpendicular to it. That's our central axis. We're going to look at a specific point on that axis, which we'll call point P. Point P is sitting at a distance of x away from the center of the ring. Now, because all the vertical forces from the ring perfectly cancel each other out due to symmetry, the net electric field at point P pushes straight out along that central axis. And that gives us our baseline equation. EP equals K times Q times X, all divided by the quantity R squared plus X squared raised to the 3/2 power. That equation right there, that's our starting line. It tells us the strength of the field at any given distance x.
You know, what's beautifully simple about this is how the messy physical world just boils down into 3 core variables that we need to track. Q is the total charge locked into the ring. R is the fixed radius of the ring itself. Those two are constants, right? They aren't changing. The only thing that is changing, our independent variable, is x. That's the distance we are standing away from the center along the axis. So everything we're about to do revolves around manipulating that one single variable, x.
Moving on to Section 2, the maximum value problem. Let's think about this physically for a second. Where exactly is the pull or the push the strongest? Well, if we put a test charge directly in the dead center of the ring, where x is 0, it's being pushed equally from all sides, right? So the net field is just 0. On the flip side, if we move infinitely far away from the ring down the axis, the force just fades away to 0 as well. So since it's 0 at the center, and 0 at infinity, there absolutely must be a sweet spot somewhere in the middle where the field swells up to a maximum peak before dropping off again. But where is it?
To find that exact mathematical sweet spot, we need the ultimate tool for finding peaks and valleys, calculus. Specifically, we need to take the derivative of our electric field with respect to our distance variable, x. See, when a value hits its maximum peak, its rate of change momentarily pauses. It stops going up, and it hasn't started going down yet. Therefore, the slope of the tangent line at that exact peak is completely flat. So in calculus terms, to find a maximum peak, we must find where the derivative equals exactly 0. dE over dx equals 0. That is our master key. Which brings us to Section 3, setting up the derivative. Okay, notice the bold purple text, to find max value. Just below that, we translate our physical concept directly into pure math. EP over dx equals 0. Now, let's look at the red ink. We're substituting our massive electric field equation in for EP. We're basically taking the derivative with respect to x of this huge fraction, x divided by the quantity r squared plus x squared to the 3/2 power. Now, because we have a variable up in the numerator and a variable function down in the denominator, this means we've got to break out the quotient rule. The bottom expression shows the very beginning of that quotient rule expansion. We've got our denominator multiplied by the derivative of our numerator minus our numerator multiplied by the derivative of our denominator. Let's actually track how this builds step by step, because understanding the underlying structure is crucial. Step 1 was establishing our condition for a maximum, setting the derivative to 0. Step 2 involved a little trick, recognizing that constants like k and q don't actually affect where the peak occurs, so we can essentially ignore them for the derivative calculation and just isolate the variables involving x. Step 3 is the execution, applying the quotient rule. And sure, that gives us a massive fractional equation. But remember, because this entire fraction is set to equal 0, we can just multiply both sides by the denominator, and poof, the denominator vanishes. We really only care about making the numerator equal 0. And now, the fun part. Section 4,
Solving line by line.
Look, I know this might look super intimidating at first glance, but remember, all of this intense algebra is literally just a logical tool to isolate our single target, x. Let's focus on the top block of equations, which is the numerator from our quotient rule, set to 0. Let's trace the logic line by line. First, we have our denominator, r squared plus x squared to the 3/2, multiplied by the derivative of x. Well, that's just 1. Easy. Now, moving to the second term, minus x times the derivative of the bottom. To take the derivative of r squared plus x squared to the 3/2, we have to use the chain rule. The 3/2 drops down to the front, the exponent becomes 1/2, and then we multiply by the derivative of the inside, which is 2x. That gives us that long second line. In the third line, we look for common ground. Both major terms have an r squared plus x squared component, so we can factor out the smaller one, r squared plus x squared to the 1/2 power. When we pull that out to the front, look at what remains inside those square brackets. We are left with simply r squared plus x squared minus 3/2 x times 2x. The fraction cancels the 2, leaving minus 3x squared. Line by line, these complex terms are just gradually collapsing and canceling each other out.
Let's do a quick recap of the math we just executed, because it actually breaks down into 3 very digestible algebraic moves. Step 1. We successfully applied the chain rule to deal with that tricky 3/2 exponent. Step 2. We looked for a common factor and pulled out the term raised to the 1/2 power to simplify the whole expression. Step 3. Because our total equation equals 0, and that factored out piece can never be 0, we just took the remaining algebra inside the brackets and set that specifically to 0. See? We've proven that the intimidating calculus is really just a sequence of logical algebraic moves.
So the crucial point is what happens right at the end in those final 3 lines of algebra. Inside the bracket, we had r squared plus x squared minus 3x squared equals 0. Well, that simplifies immediately to r squared minus 2x squared equals 0. Move the 2x squared over, and we get 2x squared equals r squared. Divide by 2, take the square of both sides, and boom, we arrive at this beautifully simple final equation, x equals plus or minus r divided by the square root of 2. We have our answer. The plus and minus just mean there's a maximum peak on both sides of the ring, perfectly mirrored along the axis.
Finally, Section 5, Visualizing the Peak.
We've done the heavy lifting, so let's ground this firmly back into physical reality. Take a look at this graph plotting the total electric field E on the vertical y-axis against the distance x on the horizontal axis. This brilliantly illustrates how our line-by-line math perfectly predicts the physical real world. Look at the red curve. It starts at exactly 0 at the origin, just like we conceptualized earlier. In the dead center of the ring, the field is 0. But as we move away from the ring, the electric field strength swells, getting stronger and stronger until it hits that distinct peak labeled Emax. And look exactly where that dotted line drops down to the x-axis. It lands precisely at r divided by the square root of 2, our calculated x value. After that point, as the distance stretches out toward infinity, the curve gently tails off back toward 0. The math literally drew a map of the physical world. We started with a physical ring of charge, built a mathematical model, navigated the complex calculus and quotient rules line by line, and emerged with a pristine, exact coordinate for the maximum force. I mean, it's incredibly satisfying, right? But it shouldn't just stop with electric fields. I want to leave you with this empowering thought. If we can map the unseen forces of electromagnetism this precisely using step-by-step derivatives, how else can we apply calculus to unlock the other hidden peaks and valleys of the physical world all around us? Keep questioning, keep calculating, and definitely keep exploring. Thanks for joining.